My name is Timur, and today I'm going to tell you about Materials Modeling 2.0. And if you are sitting out there and thinking, what the heck is Materials Modeling 2.0, then you are not alone. In fact, I've spent countless hours trying to find a quick way to explain it. It is so complex that we will need help from a superhero. This is Tony Stark, aka the Iron Man. And that is how Tony creates a new material. He starts from a periodic table and combines together cerium and dysprosium, atom by atom, to build a new compound. And then he asks computer a question: how will this new compound behave when you make an Iron Man suit out of it? And that's exactly how we see the future. Product design of the future is starting from the atoms, and Materials Modeling 2.0 is making it a reality. Now that is how our product looks at current. Just like Tony, we let our users start from the atoms and assemble together compounds, and then run simulations that predict the properties of these compounds. Here I'm using something called electronic band structure, which tells us how good this material would be when you make a semiconductor chip out of it. In the movie, Tony ran 465 simulations. With one of our early customers in this case study, we did 296. We took what otherwise would be 10 years of modeling and compressed that into under 2 days. They were able to screen a large data set of potential applications, alloys for potential applications in aerospace and automotive fields. Up to date, we have closed 3 Fortune 500 contracts, have about 10 other customers, potential customers in the sales pipeline, and over 100 individual users coming from places like MIT, Berkeley, and Stanford. As you already understand, materials modeling has many people and many components involved. And we are successful at what we do because we make all these people and all these components collaborate efficiently towards one goal. In an old school scenario like I'm showing here, a company like Dow Chemical would need to go and buy a supercomputer from HP, hire people who understand how to run simulations on this supercomputer, and then automate the work by writing scripts. In a more up-to-date scenario, they would use cloud computing and machine learning to speed things up, and then hire a bunch of physics PhDs to do data science. That helps, but only marginally. Because our product is end-to-end, it has the potential to cut down the time from concept to product in twofold. Back in 2015, I've met Mohammed, who is present here today, a bright computer scientist. He was just out of his PhD, I was out of my PhD in physics from UC Berkeley, and together we decided to change the way people use computers to study materials. Along the way, we got joined by some of the brightest minds in the field, including professors from UT Dallas and UC Berkeley, as well as successful entrepreneurs. Up to date, we have raised close to $1 million from the 3 parties I'm showing here, and we'll be ready for the next round of conversations in early 2018, after closing a milestone contract with our key enterprise partner to date. We'll use the next generation funds to take our work to production use with a set of early customers. All right, let me summarize here. exabyte-io partners up with companies in the Fortune 500 range to drive the digital transformation of materials and chemicals R&D by applying a patented Tony Stark approach and making material scientists more efficient. In our vision, the next generations of semiconductor chips, petroleum catalysts, and car batteries are made not through long and expensive physical tests, but through fast and accurate models. Thank you.